In this video, we are going to understand the concept of modulation. So, first of all, the very first question which comes in our mind is what is modulation? So, basically, modulation is a process by which we change the characteristic of a high frequency signal with the instantaneous value of the modulating signal, or you can say with the instantaneous value of the information signal which you want to transmit. So, basically, information signal is a low frequency signal and you need a high frequency signal which is known as a carrier signal. So by combining both the signals, we change the characteristic of the carrier signal, which basically carries the information. So that is basic information, or you can say basic definition of modulation. First we will say what type of modulation you achieve. So basically modulation can be categorized into two types. One is linear modulation, another is angle modulation. So in linear modulation, amplitude modulation is the category or the concept. Whereas in angle modulation, we have two types of modulation. One is known as frequency modulation, another is known as phase modulation. So basically modulation can be divided into two subcategories, and in those categories there are three basic types of modulation, as in amplitude modulation, frequency modulation and phase modulation. Now this is a very simple you can say representation of a signal A cos theta, any sinusoidal signal. So A cos theta contains two terms, which is A and theta, where this A is the amplitude and theta is the angle. So what you can do, you can keep the theta constant, that means you can keep the angle constant and change the amplitude. So by changing the amplitude, you can achieve amplitude modulation. And another thing is you can keep the amplitude fixed, that is A you can keep fixed and change the angle theta. So this theta is basically omega ct plus phi, that is, it contains two terms, one is frequency, another is phase. So by changing the theta or by changing the angle, you can change two characteristics, angle and frequency and phase. So out of these two, at a particular instance, or you can say at one time, you can change any one quantity. So either you can keep the phase constant and change the frequency, or you can keep the frequency constant and change the phase. So by that you can achieve two other types of modulation, which is frequency modulation and phase modulation. The basic introduction of modulation is this. Definition I have already explained you. That means this is a low frequency signal. This is, you can say, the modulating signal or the information signal which you want to transmit. This is a high frequency signal which is basically used for the purpose of modulation. And this is, the third diagram is basically the amplitude modulated signal. So in amplitude modulated signal, what you can see, this is the carrier signal. That means under this waveform you can see the carrier signal, and here the amplitude is constant, but now the amplitude is changing according to the amplitude of the modulating signal. This is what the definition. So this is how amplitude modulated signal is achieved. So basic concept of modulation I hope you must have understood. Now why we need modulation? This is the second question which comes in our mind. Can't we send the signal directly without the modulation? So the answer is yes, we can send the signal directly without modulation, but there are some limitations. That means for a longer distance you may not be able to transmit the signal. So for that you need modulation. So what are the other reasons that we need modulation? This is the second part of this video. So let us see what are the need of modulation, why we mix a high frequency signal with a low frequency signal or with our information signal for the transmission. That is the question which comes in our mind, that is need of modulation. So answer for the need of modulation, now I will explain. This is a very important question as far as exam is concerned. In exams, many of the times they need what is the need of modulation, or even in the Viva, the externals ask what is the need of modulation. So these are the various points for the need of modulation. The very first point is height of antenna. So you must know that there are antennas for the transmission and reception of the signals. So you have to build an antenna for the transmission and the height of antenna formula is h is equals to c by lambda, where c, you know, 3 is into 10 raised to the power 8 meters per second. So c by lambda can also be written as c by 2f, where f is the frequency of the transmitted signal. So let us say we want to transmit a 1 kilohertz frequency signal. So instead of f, I have written 1 into 10 raised to the power 3. So by calculating this, it will come out to be 150 into 10 raised to the power 3 or 150 kilometers. So that means if you want to transmit a 1 kilohertz frequency signal, you need to build an antenna of 150 kilometer height, which is not practical or which is not feasible. So for that, what we do is we mix this low frequency signal with a high frequency signal. Suppose this 10 raised to the power 3, that is 1 kilohertz signal, can be converted into 10 raised to the power 6, that is 1 megahertz. So this 150 kilometers reduced to the 150 meters. So an antenna with a height of 150 meters is achievable or practical. So height of antenna or practicability of antenna is the first aspect of our need of modulation. I hope this example gives you a better idea of the concept of height of antenna, why we need modulation. Otherwise, it is not practical to, you have to maintain a 150 kilometer height antenna, which is not possible. Another point is narrowbanding. Like for example, if you want to transmit 1 kilohertz frequency at a particular instance, and at some other instance you need to transmit 10 kilohertz frequency. So the ratio of these two frequencies 1:10 without modulation. So that means a single antenna cannot be used for the transmission of two different frequencies because the band is very large, the band gap is very large, or the ratio is 1:10. So what you can do is you can modulate this signal with a megahertz frequency. So it will become 10 raised to the power 3, that is 1 kilohertz, plus 10 raised to the power 6 or 10 raised to the power 4, that means 10 kilohertz plus 10 raised to the power 6. So when you check the ratio of these two, it is almost or nearly equal to 1:1. So that means one single antenna will be useful for the transmission of two different frequencies. That is what the concept of the another aspect, which is narrowbanding. That means the bandwidth gets narrowed by modulation. Without modulation, the band gap is more or large, so that a single antenna will not be useful for the transmission of multiple signals. So that is what the second concept of need of modulation. And the last but very important aspect is multiplexing. So this multiplexing is basically three types. First, I will tell you the definition of multiplexing. Multiplexing means simultaneous transmission of multiple signals. That means through a single communication channel, you are transmitting more than one signals. So what happens if you transmit more than one signals through a common channel, and if the frequency difference of all the signals are less? Suppose you are transmitting 100 Hz, 110 Hz, 120 Hz. These three signals you are supposedly transmitting simultaneously. So what will happen when you transmit these signals simultaneously? They will mix with each other, and at the receiving end you will not be able to extract the signals properly, because they will be mixed with each other in so much depth that you will not be able to extract those signals because of their frequency difference, very low frequency difference. So what we do is we modulate those signals with high frequencies. So now what will happen? The frequency difference between all the signals will increase. So now you will be able to demodulate or extract those signals at the receiving end. I can explain you this thing with a simple example. If you mix wheat flour with something very, or you can say gram flours. So if you mix both the flours, it is very difficult to extract both because they are almost of the same frequency. But you mix with wheat flour with rice, you can easily separate because the gap or the density or the difference of size is separate. So it is very easy to distinguish both the items at the receiving end. Same way, frequency plays the same role. That means they can be separated easily if they are having a huge frequency difference. So on the basis of their criteria, I have divided the multiplexing in 3 types. One is frequency division multiplexing. In this, we are dividing the signal on the basis of their frequencies. Another is time division multiplexing. In this, we are dividing the signals on the basis of time. That means we will be allotting them the different time slots. Third is wavelength division multiplexing. Wavelength division multiplexing and frequency division multiplexing conceptually are same, but only difference is in frequency division multiplexing for the transmission we are using copper wire, whereas in wavelength division multiplexing we are using optical fiber. So in this frequency division multiplexing, signals are transmitted in the electrical form, and in this wavelength division multiplexing, signals are transmitted in the form of light. That is what the basic difference. Otherwise, the concept of both the transmissions are same. So this is what the concept of multiplexing. So in need of modulation, you have to explain these 3 things. First is height of antenna, another is narrow bending, and third is multiplexing. So this is the basic of modulation. Now we will see the mathematical derivation of amplitude modulation. How mathematically you can derive or explain any amplitude modulated signal. Let us see the mathematical derivation of amplitude modulated signal. So in amplitude modulated signal, we are having 2 signals as per the diagrams we have seen. First you have a modulating signal. So let us say Vm is equals to, small vm is equals to capital Vm cos omega mt, and small vc is equals to capital Vc cos omega ct. The first signal represents the modulating signal, another signal represents the carrier signal, where Vm and Vc are instantaneous values of amplitude of modulating signal and carrier signal respectively. Capital Vm and capital Vc are the maximum value of amplitudes of modulating signal and carrier signal. And omega m and omega c are the frequencies of modulating and carrier signals. So we have assumed these 2 signals. Now the amplitude modulated signal can be represented by Vam is equals to capital V cos omega ct. As you have seen the diagrams, this was the diagram I have drawn. So this is the frequency, which is the frequency of carrier signal. So this should be cos omega ct, but the amplitude is basically this plus this. This is what? This is the maximum value of the carrier signal. So we have kept capital Vc, and then this is the instantaneous value of the modulating signal. So capital Vc plus small Vm. Again, this part is the maximum Vc, maximum value of the carrier signal, and then after that it varies instantaneously according to the value of modulating signal. So capital V can be replaced with capital Vc plus small Vm. This is what the amplitude of amplitude modulated signal. So this Vam now can be represented by capital Vc plus Vm cos omega ct. So by opening the bracket, you can get Vc cos omega ct plus Vm cos omega mt cos omega ct. Small Vm can be replaced with capital Vm cos omega mt, and then this cos omega ct. So this is Vc cos omega ct plus this is cos A cos B, that is cos A plus B and cos A minus B. So this is half Vm cos omega c plus omega mt plus half Vm cos omega c minus omega mt. So by calculating the mathematical derivation, we obtained the amplitude modulated signal Vam with this expression, which contains 3 terms. The first term is the carrier signal. As you can see, this is Vc cos omega ct, nothing but the carrier signal. Second and third terms are the upper sideband and lower sideband respectively. This part is known as the upper sideband, which is having frequency omega c plus omega m, and this is the lower sideband, which is having the frequency omega c minus omega n. This is what the diagram of AM in frequency domain. This diagram representation is of time domain. This diagram is of frequency domain. So in frequency domain, this is the carrier and these are the two side bands. The inner part is known as the LSB, that is upper side band, and the outer part is known as the upper side band. So this part is the upper side band and this part is known as the lower side band. So this is the frequency domain representation of AM signal. So if they ask in the exam the mathematical representation of AM, you have to derive the mathematical representation of AM in this way. Okay, so I hope you understand the concept of AM, which is having three components. Now in the next video we will be having the concepts of DSB and SSB, that is double sideband and single sideband. Moreover, we also discuss about the modulation index of the amplitude modulated signal. So I hope in this video you must have understood the concept of modulation, need of modulation, as well as the mathematical representation of AM signal.